this video, we will continue with our introduction of causality and looking at causality through causal graphs. And we will talk about two common problems in applied econometrics in virtually any causal inference that are hard to detect when we use a potential outcomes framework, but are very transparent and become very obvious when we use DAGs. This goes especially for colliders, bad controls you can detect in either framework. So what are we talking about here? Let's start with colliders. You may have heard of bad controls before. If you're not, don't panic. You will hear about it in this lecture, but you probably haven't heard of colliders before. And they are actually an important source of bias because people are not aware that that bias could be there. So what is a collider? You can see here a collider is this variable x here, whereby that variable is determined both by the treatment and by the outcome. And when that happens, when you have such a variable, strange things can happen if you include this variable in your estimation. Why is there such a big problem? Well, the problem comes because if you look at this second picture here, where you have no relationship in your model between the treatment and the outcome, yet because both determine x, you can induce a spurious correlation between the treatment and the outcome if you control for x. Right? So we always learned in undergrad and master's level econometrics, we learned control for anything you can possibly find, just run a kitchen sink regression, because that controls for all sorts of confounders. But one big problem is that you actually may be conditioning on a collider and thereby introduce a bias. And I will show you that this bias can be there, especially when we choose certain types of samples. That's when this collider bias can oftentimes be inbuilt. So let me show you here one example of a DAG where you have a collider. So what you have here again is we have our relationship between the treatment and the outcome, our treatment effect that we're interested in, and we have two confounders. And these confounders U1 and U2 are unobservable to us. But what is observable is the variable I. I cannot really provide an example here, but you could easily see how these type of these type of constellations of different variables could occur in one context or another. Okay, so you don't observe the confounders that you would want to observe, but you observe a variable that is correlated with the confounders. Isn't that great? You can actually, you could then include that as a proxy and you're done. Right? Your potential outcome framework would probably tell you that's what you should do. But when you look at a DAG, you will immediately see that this is not the case. So let's go step by step. We have to again look here at all the different backdoor paths and see, are they open or are they closed? Okay. And the ones that I pointed out here, there is obviously a good few backdoor paths because in this model, besides the direct effect from D to Y, you have those indirect effects via U1 and via U2, but then you also have these longer paths, which is from D to U2 to I to U1 and to Y and the other way around. So first to U1, then to I, then to U2, and then to Y. Right? So these are the orange path, the one that I just outlined here is the one you can see here. And what you see when you write down this causal path is you have a variable in which where both arrows point to the variable. That's a collider. Okay? So here I is a collider. You see those two arrows, those two blue arrows coming in here. Now I'm drawing them in red so you can distinguish them from all the other scribbles. And you can see them, you can see that here and obviously in the other path as well. Okay, so the challenge here is we want to actually eliminate the confounding influence of U1 and U2, but we don't observe them, we only observe I, and so let's just control for I because it's correlated. And the problem is we can actually make the problem worse, as in we introduce a bias because we actually control for a confounder, control for a collider, and that actually opens both backdoor paths. So we say that if, let me just tidy this up a little bit, that those two backdoor paths that you see here are closed because there's a collider on them. They're closed. Okay. And you can also see this here in the graph. I in this case does not help us deconfounding the relationship between D and Y. Right? What we would need is we would need to eliminate these two arrows here, and we would need to eliminate these two arrows here. How would we do that? By controlling for U1 and for U2. But controlling for I, we can clearly see, will not help us getting rid of these arrows that we want to get rid of these confounding influences. And what's worse is it introduces this bias because it actually it opens up additional paths through which the treatment, the path from treatment to the outcome can be confounded. Now this may all sound super abstract to you, and I can't blame you for that. So let's start here with an example that is admittedly a bit silly, but gets the message across quite well, I find. So this is from the Causal Inference mixtape, and there is the example Cunningham gives here is to say, you know, we have a correlation when we look at movie stars. We have a negative correlation between talent and beauty. So they're either super talented, but then they're not that beautiful, or vice versa. Yeah? And does that tell us anything about talent and beauty in the overall population? That's the question. Okay, so imagine, you know, you're talking to some friends and they say, oh well, you know, there is typically a negative correlation between talent and beauty. Just look at movie stars. They're always either talented or beautiful, but hardly ever both. And now suppose that these that in the population this is actually not true, right? That there's no reason why the two things should be correlated. But if you observe them in a specific sample, that may actually be the reflection of collider bias rather than a true relationship. Okay? So what happens very often in applied research is we don't take the full population, but we take a particular sample, like a particular group, and because we observe that particular group, we may, or by using only that particular group, we may actually introduce collider bias. And that's the example here. So suppose these two are not related, which is what you can see here. There is no arrow between talent and beauty, but talent determines whether someone is a movie star, and beauty also, to some extent, right? On average, there's probably people who are considered more beautiful have a greater chance of becoming movie stars for whatever reason, right? And then the talent in acting and selling yourself and whatever other talent you need to become a movie star is certainly a determinant, right? And so now if I pick the sample of movie stars, I will then see that in that group, I have that negative correlation. And is that a reflection of a true relationship, or is it simply part of the selection process into that profession? And as we see, there is not even among movie stars that negative relationship would be in any way true. All that is there is that it reflects the fact that we slice a particular part of the overall population. So what is it? In order to understand that, what is that part of the population? In order to understand that, we need to have a model in mind for selection into that profession. Okay? And so what the simplest possible model would be a threshold model, whereby we add up that a person's score in terms of beauty and in terms of talent, and then say, okay, with that overall score, only the top X% become movie stars. Right? So you have to score pretty high overall to become a movie star, which is obviously a very simplistic model. You could think about way more complicated ones, but that's not the point here. The point here is that if you think here about two axes, so you have beauty here on the vertical axis and talent on the horizontal axis, given that rule, in that case the top 15%, we would have, first of all, we would have the total population here, but when we slice them into to those who become movie stars and those who don't, well, if the top 15% are becoming movie stars, then we're here. And you can clearly see that while in the total population you have virtually no relationship between the two, it's very clear that just by taking this slice of the data, we all of a sudden have a negative relationship. Right? And a lot of people may simply not be aware of this bias, because it's, you could obviously say, okay, this is I want to do a study that is representative of movie stars, then that's probably not a problem. But if you want to do a study that is representative of the broader population and say, here, I have data on movie stars and look, that's what I find, you actually have to live with or deal with the fact that you have a collider bias problem. So that's an issue, and that's something that you need to be aware of when you study any type of group. You pick a certain type of firm. You only pick large firms. You only pick exporters. You only pick certain groups in the population. Only a certain profession. Only a certain group of students. What you observe within that group may not extrapolate to other parts of the population, and not because that group is particularly unrepresentative per se, but simply because due to that selection into that group, you have a collider bias. And that comes on top of that group not being representative to begin with. Actually, in the end of this slide deck, you will see, now you may say, okay, is this really something that collider biases, is this really something that occurs very often? It sounds all too either trivial or too obvious to be a problem. And it turns out it's actually quite common. And so here is a recent paper by Eric Schneider, who's an economic historian and who looked at collider bias in economic history research. And what he does very well, he points out 10 studies that are very well published that have a collider problem, but also where the authors solved it. So it's not to say, okay, you know, look at those authors, they all ignored that point, but they actually solved this problem successfully, and he explains what the problem is, how they solve it, and so on. So I highly recommend that you have a look at that to also to get a feel for where the problem typically collider problems can actually appear. Okay? Invisible sample selection is one, but then people may just throw in all sorts of control variables into a regression that may also introduce collider problems. Now, another problem that is more obvious, but yet lots and lots of people make a mistake not accounting for, is the so-called bad control problem. So here is an example from that was given in a blog post by Marshall Burke, who either did a study or cites a study, I'm not entirely sure anymore, that looks at development economics papers. So papers that look either at natural resources or things like temperature and conflict, or conflict and economic growth. There is obviously a large literature surrounding these topics. You know, what are the causes of conflict and what is the effect of conflict on economic outcomes? That's obviously a very, very important subfield in development economics. Problem is, you find a lot of studies who do something like that. So this is, for example, a study that would want to look at the effect of temperature on conflict. So the idea is, if you have huge spikes in temperature, you may get droughts, and then that may affect then the likelihood of there being a conflict because there is scarcity of basic nutrition and so on. And now suppose you have a panel of countries, or a cross-section of countries, of developing countries, where you can measure that. Now someone comes in your seminar and says, oh, but you know, those different countries, they also have different incomes. So you should adjust for that. And you would not, you'd be surprised how often you would hear that. And even nowadays, I always present the way I do here with, you know, being able to draw and so on. Even if you show them a DAG, they would still say, no, but you need to adjust. The problem is, what's going on here is that you adjust not for a confounder, but for a mediator. At least if this is the model, if this is the true model. And what does this mean? It means that temperature determines income, especially in countries that are heavily dependent on agriculture. This is probably true. And that income then has an effect on conflict. So you have two paths here, a direct one from temperature to conflict, and an indirect one through income, right? And so now if you control for income, you actually bias the relationship between temperature and conflict that you're actually interested in. And so therefore that is obviously a huge problem. And so the problem here is that usually by controlling for variables, we want to do away with selection bias. Okay? We want to deconfound the relationship that we want to quantify. But here we do actually the opposite. So with that good intention in mind that we actually want to reduce selection bias, we actually make the problem worse. And so here the cure can be a lot worse than the disease. So we have to be really, really, really careful. And so this problem has been around for a long time and has been known. And so while I believe, you know, people can be forgiven for not spotting a collider problem because that's less well known, with a bad control problem, it's different, right? So this is just a grave mistake. This is just as if you just assume there is no selection bias in an observational study. It's just a grave mistake in research design, but one that can be easily avoided. When we control for variables in a regression or in a matching framework, we want to do away with selection bias. The problem when we condition on a mediator is that we actually introduce selection bias. And so we can actually make the problem a lot worse. The problem here is that, as I've shown in this, or as we've seen in this graph, in this DAG, income is a function of temperature. So it's not randomly assigned to countries, but it's determined among other things by temperature. And we just assume here in this DAG that other things just don't matter, just for the moment. And so here, countries presumably with a higher temperature have a lower income. Now, we can think then about what is the sign of the bias here in this case. And admittedly, for determining the sign of the bias, it's oftentimes easier to do this actually with potential outcomes. So here is really where potential outcomes, I believe, are much easier to work with. But let's do it anyway with the DAG. So the DAG is actually useful to just, first of all, spot and also communicate to others why there is a bad control problem. And as I said, unfortunately, this problem has been around for a long time, and too many economists ignore it altogether. And that's a huge problem, and something that, unfortunately, even the generation of economists that are watching those videos will still have to deal with in years to come. So let's assume that the direct effect of temperature on the likelihood of conflict is positive. I've written initially negative, but it should actually be positive, right? So if you have those spikes in temperature, that should make, there is good reason to believe that this leads to scarcity and conflict over resources, because there is, for example, less food available, and that increases the likelihood of conflict. However, there is also another effect, which is this indirect effect that temperature will probably reduce income. So higher temperature, means that you have a worse harvest, and you can export less. That should lead to a reduction in national income. And when you have lower national income, regardless of the direct effect, you should also have lots of other reasons why there is more conflict, why that leads to more conflict. Simply because more people are unemployed and there is more potential for conflict. Right? And so when you put all these things together, you have a positive direct effect, but you have this negative effect of temperature on income. Then what it means taken together, if we do this here, so you have a positive effect here and a negative effect here. Once you condition on income and you simply run a regression or do a matching, and to quantify the relationship between temperature on the right-hand side and conflict on the left-hand side, the coefficient that you get will be downward biased. And I show you here a simulation with 10,000 times the same model simulated. Okay, so the idea here is that we have a regression of conflict regressed on beta temperature plus epsilon. So we are interested in this coefficient beta here. Okay, so what we do here is we simply assume that the true beta is 0.054. Okay? That we assume, and then obviously we add some noise to the model and simply simulate this model, or simulate this data set 10,000 times. So the idea here is that with each simulation, we draw temperature randomly, and then we draw epsilon randomly, and we make assumptions about alpha and beta. So alpha is this down here, and that's beta. We make assumptions about those, run the same regression 10,000 times, and then see what the average effect is. Okay, so that's what we get here. Now in the second simulation, we run the same, we simulate the same data set, but we condition on income, which is a function of temperature, and also has an effect on conflict. So what we do here is basically the following. So in terms of the protocol, what you would do is the equation up here would be your data generating process. Okay, so we simulate a data set with those characteristics 10,000 times, and then each time we run a regression of conflict on temperature. That's what gives us the result in column 1. In column 2, we do the same thing, but we simulate this data set, this data generating process 10,000 times as well, but now we run a different regression. The regression we run is the following. So the regression is, I'm just gonna use the abbreviation C. C equals alpha plus beta temp plus gamma income plus epsilon. Okay, so we assume that the data generating process, that's the true model, but this is what's going on in the real world out there. But we run a regression where someone in a seminar audience told us, yeah, but you have to control for income here, because how can you not condition on income, because countries have different income and that determines conflict. But it's an endogenous variable here, right? And so we simply, the way we would have done this is we would generate first, draw randomly the temperature, and then have income as a deterministic, or as a part deterministic, part stochastic function of income. So we would have an auxiliary data generating process whereby income is a function of temperature, and we would simply make some assumption about these two delta parameters. Okay, and so what you see here is that, as expected, we would get a downward bias in the coefficient, and that's, in this case, is constructed in such a way that it would go down by about 20%. So it's 1 percentage point in that elasticity. So that's, obviously it depends on the context, but can be quite a lot. And bad control problems are everywhere. And if you don't believe it, you can just once you go to seminars, you see there's a lot of discussion about them. And while there should be a lot of discussion, in my view, about selection bias due to confounders, there should be no discussion about bad controls. Bad controls are what they say. They're bad. They should not be included in the model. There is, I'm not sure if we get to it in this course, but there is a way to analyze how big this direct effect here is and how big the indirect effect is, and that's called mediation analysis. That's a very different type of technique, and that's if you're interested in disentangling those channels, which undoubtedly is very important, you need to use these techniques. But just controlling for a mediator will not get you there, and it will even make the problem a lot worse. Right? So in the live lectures, we will talk about an example that is racial bias in policing, where economists and political scientists typically run regressions that try to show that blacks are more often convicted of a crime than whites, and to what extent does this reflect racial bias. But as we will see, there is a bad control problem here that is not so easy to spot. But once you have a DAG, it actually helps to make this problem transparent. So what's the main takeaway from this? The main takeaway from studying causal diagrams is they are very, very useful. They're useful for research design because they clarify which variables we should, and perhaps most importantly, which we should not control for. And so if you've ever been asked to run a so-called kitchen sink regression, just throw in whatever control you can find in your data set, forget about that. Think very carefully, what is the relationship I want to study? What is the minimum set of variables that I need to observe or deal with, because I can't observe them, in order to identify that causal effect of interest? So this is a theoretical tool. And it's not a theoretical tool like you've learned in microeconomics that involves some sort of optimization and involves modeling behavior. It's actually a lot simpler than that, yet it's a theory. And it's an important theoretical tool that if you don't master, you will have a hard time providing a convincing analysis in whatever empirical study you're doing. And there are three main messages about what variables you should include in a regression or also in matching. First of all, if there is a confounder, you have to control for it or deal with it in some other way if you don't observe it. But you have to address it. Then, if you have a collider, do not control for it. Otherwise, you introduce bias. Collider problems are not that obvious, but watch out for them. They exist. And the third one is, if you want to or are asked to control for a mediator, don't do it. Even if a referee asks you, show them the regression in the response letter, but do not include this in the paper. I want to go as far as to say, if you want to get a PhD in economics, do not ever do that. That's a beginner's mistake, and it's something that is unforgivable because it has been around for so long and known for so long. But just to reiterate, do not ever condition on mediator. If you want to analyze the role of mediators, you need to use the toolbox of mediation analysis that is slowly coming into economics, is much stronger in for example, political science. So if you are interested, I can certainly point you to studies that introduce these techniques in an accessible manner. Okay, so how should we then use causal diagrams in an analysis? Should they be in every paper? The answer is no. In most papers, the identification of a causal relationship through the techniques we learn, it's so clear what you should condition on and what your identification assumption is, that you will not need to explicitly state it in the paper, or that you will not have to make it explicit in the paper what the causal diagram is. So the way you should use this is how writers use a character map. right? So, which is also something you don't see when you read a novel, but they have in the background a map that shows them how all the characters, how all the protagonists are interlinked as you go through the novel, just to keep everything consistent. In the same way, you as the researcher should use DAGs and simply show to simply get an understanding yourself, and in order to produce a convincing research design that allows you to convincingly uncover causal relationships. Now, if you want to do some further reading on this topic, here are 3 recommendations. The first is Guido Imbens has put together a review article where he critically analyzes this debate that has been going on Twitter for quite a while about which approach is better potential outcomes, which is preferred by economists, versus DAGs, which is preferred by computer scientists. And obviously, my take on it is both have their advantages and disadvantages, so it's important to know about both. DAGs are less popular in economics, but will become so over the next couple of years, I'm almost certain. Then Montgomery et al. Have a very nice paper on bad control problems in experiments, mainly addressed at political scientists. So they use a lot of examples from field experiments in political science and what can go wrong if there are bad control problems. And it's very, the writing is very accessible, so I can highly recommend that. And I already mentioned Schneider's paper on collider bias in economic history research, which shows you very well that collider bias is real, and you can find it in more applications than you would actually think.